All right, so my name is Dominic. We're going to be talking about MPD applications for high pressure, high temperature wells. All right, so first we're going to talk about the equipment used. So there's two main components that are used with the MPD system. It's the RCD and the dynamic annular pressure control system. The DAPC, it includes an automatic choke manifold, back pressure pump, the flow meter, and a programmable system. And this system is used to manage constant bottom hole pressure. And it does this when drilling, tripping, making connections, and conducting dynamic inflow and leak-off tests. It's also used for wellbore stability, and you can check on equilibrium between the BHP, pore pressure, and fracture gradient. And another cool thing we'll go into later on is this system. It requires fingerprints from certain people, so then it's easier, not easier, but more secure to log into. So the RCD, this includes a locked sealing element, a riser containment system, and a side outlet spool. The spool contains the returning fluid and then directs it back towards the choke. The control system, it tracks data regarding surface annulus pressure, flow rate, choke position, fluid density, and key drilling parameters. And when changes occur, it makes real-time calculations of the bottom hole pressure. So then in turn, since you're making real-time calculations, the controller, he can calculate the amount of back pressure required during whatever specific time they need. And when selecting equipment, you need to select pressure control equipment. One must evaluate various aspects of the equipment, but for sure the pressure rating. But I don't know if y'all remember on Monday, a lot of the newer systems I was talking about, the manufacturers don't really have a lot of pressure ratings info yet on them. And emphasis when selecting everything, it has to be put on the RCD element, and this must be checked in conformance with the API specifications. And due to the fact that the max internal pressure of the RCD is designed to contain will depend on each operation. So there's different specifications for various pressure ratings, and the three most popular, the three main ones are the dynamic, stripping, and static. And although these, they're the three most important to consider when to complete the RCD selection process, they're not the only things you need to consider. All the pressure ratings are for the new sealing elements, and you have to consider physical wear, and that's unavoidable. And there's also risk when considering the mud and the nature of the high pressure, high temperature well. And to select the most appropriate seal, there's tests that are run under static conditions in the lab. The mechanical conditions of the pipe and rig equipment must also be considered due to potential damages that may occur. But it's not really, you can't really test these damages, because you'd have to be testing when you're actually under actual conditions, and so it's not really practical. At or above the surface pressures of 500 psi, it made it necessary to evaluate procedures for running testing and to maintain the equipment. And these procedures described that the pressure test for the RCD and those that ensured integrity of the seal were the most important. And any loss in that integrity could cause a loss in early kick detection. So that's very crucial right there. And there are many indicators that show a seal is being compromised. There's direct and indirect, but only very few you can really see. One of them is when the back pressure drops when the choke is closing or after it's closed. And a steady drop in annulus pressure after the choke is closed is another indication of loss of pressure and possibly a leaking seal. And if that is the case, it requires immediate action to see what's going on and fix that before anything else. Now, the equipment selection, it can't be completed until the footprint of the equipment is matched to the spacing on the rig. And the footprint is very critical for installing the RCD housing. And so right here, this figure is just a diagram of once the equipment is selected, one must complete this diagram. It's called the piping and instrumentation drawing, and all the ID is based on results of rig survey given by the provider. And once you do this, it has to be signed off and validated before any operations can even begin. So now we're gonna get into the procedures of actually drilling in high pressure, high temperature wells. Using the equipment for the kick detection is not dangerous. What is dangerous and can provide challenges is the mitigation of risk as it improves kick detection efforts in OBM, where any potential influx of gas would be highly soluble in making the kick detection challenging. And when identifying a kick detection, there are three main indicators: is that the flow when it pumps off, pit gain, and an increased inflow. So unfortunately, though, there's a small influx in solution may not be detected until gas breaks out of solution near the surface. So in turn, conventional flow checks may not identify an influx while kick is at the bottom and in solution, which could possess or propose some serious danger. And so right here, when we see this figure to the left, the shaded area represents the transition times from when the mud pumps are being brought offline to make a connection as back pressure is increased until the BHP can remain constant. And so this turquoise line we see right here represents the flow in. So you see how it decreases, remains steady, then increases. This orange, it represents the flow out. It also kind of decreases, increases, kind of steady-ish, and goes back up. And the red just represents the back pressure. So this figure right here is going to be the total gains of the versus the flow rate. And so this highlights just the normal trends for pit gain, where pumps are staged down from 500 gallons per minute, and back pressures are actually staged up to hold the BHP constant. And so in theory, the decompression trend lines, they should be uniform and follow the same decompression profile, but obviously when you're actually drilling in, that never really matches up. And so this emphasizes the need to take a fingerprint, which I was talking about earlier on, with each connection, and this allows personnel to analyze and collect data. And so during execution, there were two situations that were identified when flow check procedures would be required to evaluate the primary well control barrier. In these situations, they were termed static or dynamic. And so during the static MPD equipment, the equipment is lined up to the trip tank. And from this picture to the left, we can see it's so it's it just represents how everything is being lined up with the time versus the PPG, and then we see the pressure also on the right. The service provider increases the back pressure to hold a constant BOP through the use of DAPC pumps, but once the mud pump is offline, the surface pressure is actually equal to the total annulus friction pressure felt on the bottom of the hole while drilling, and continuously circulating in a closed loop system. But while the service provider is circulating, on trip tank, back pressure is staged down in pressure increments. So right here we see how it's each little increment is staged down and goes down and goes down. And at the same time, though, the trend is maintained for stabilization by the meter. And so for dynamic, the flow check procedure is comparable to a conventional flow check, just basically without the MPD equipment. The flow rate is also staged down, we see right here, in gallons per minute while the MPD remains completely open. Each gallon per minute stage is monitored for trendline stabilization as well, just like in the static procedure. But in static, the static and gel levels have a potential to suppress a low intensity influx. And since dynamic, moving, the drill stream, it continues to rotate, and the mud is in constant rotation. So because of that, the gel strength is being constantly broken down. And so to complete the various flow checks, static or dynamic, we have to have an accurate measurement of flow in volume, the calibrated Coriolis meter, and an accurate PVT equipment. If the meter is not installed on the flow side, however, it must be calibrated with rig pumps prior to drilling out, and the shut-in process still remains the exact same. The equipment proved useful for maximizing all trips. In high pressure, high temperature wells, there is a high potential to swab in an influx during routine tripping operations. but to offset swab, back pressure is applied to maintain constant BHP. And this is a primary key job responsibility for field drilling engineers. And so at the end of all these, everything, all the gathered results, basically came to the conclusion that while drilling the original wellbore, the MPD equipment was employed with mixed results. The varied results came from the limiting of MPD procedures that were implemented during drilling, and the lessons learned from primary well were used for MPD procedures and for a sidetrack well. Sorry about that typo. And although kick detection is primary concern, the BHP was still held constant to understand the relationships and trends within the wellbore itself. We found 3 significant advantages. There's a detection of small influxes via the meter, implementation of managed pressure stripping procedures, and also an application of MPD techniques that reduce the circulation and managing entrained gas at the surface. So when they started talking about this detection of small influxes within these high pressure, high temperature wells, we found that there were small volume influxes were detected and they were mitigated though through the use of the MPD equipment by following procedures in a high pressure, high temperature environment. The well was shut in once any abnormalities were detected. This little table right here is basically breaking down the trip efficiency. We see right here the well bore, trip speed, mud weight, and then this is with back pressure, 300 psi. This is without. So we see how when we do apply back pressure of 300, the lines, it starts to you see just different trends going on. And so the MPD stripping procedures to utilize to maintain BOP constant while pulling out whole. The ability to offset swab increased strip efficiency, allowing stem to be extracted at a more efficient pace. And this kind of blew my mind when I was reading this. But so with MPD of just a 300 back pressure, with a 28,900 foot well being drilled, it went from 31.3 hours to 24.2 with 300 back pressure applied. And this time equates to saving approximately 65 to 75 grand for the company. So just with MPD saving 6 hours, it saves a lot of freaking money for everyone. And the 4 lessons that were learned when reading everything was that planning, equipment specifications, procedures, communication meetings, RCD sealing elements, bearing assembles, and the DAPC pumps, like those are all the most important things that need to be planned and basically talked about before even drilling to have a successful operation. And in conclusion, basically, MPD equipment and techniques, they can be applied successfully to high pressure, high temperature wells to mitigate challenging kick detection